So we're going to talk about the normal distribution today.
That's awful.
And I'm going to use an example of a distribution that I think is normal, that I've heard is normal, and we'll have to talk later on about if we have a distribution that we don't know is normal or not, how can we decide if that distribution is normal? So kind of right now I'm just going to go over some of the theory of the normal distribution. So I've heard that the distribution of SAT math scores is normal, so I'm going to use that for my example. So I'm going to define a random variable, which is a variable that takes on a numeric value. So I'm going to say x is the value of one random student's math SAT score. So this is the value of one student's math SAT score. So obviously, I mean, for all of the kids that take a particular SAT test, I could randomly pick one x value and I would get a number between, I believe, 200 and 800. And there's obviously some variability there. Some kids will get, on the lower end, some kids on the higher end. But if the distribution is approximately normal, what does that mean? So a normal distribution is going to look symmetric and bell-shaped, and it's centered at the mean. So those are kind of the key properties here. So if something is normal, it's going to be symmetric. It's going to be bell-shaped, and we'll just have to I'll draw the picture so we can see kind of what that means. And it's going to be centered at the mean. Okay, so math SAT scores typically have a mean of about 500. So that's the mean of all SAT scores. That's mu of x. So that's the population mean, that's the parameter. Remember, a parameter is a number that describes a population. So that's the mean for like all students that take a particular SAT test. And the standard deviation is usually about 100. That's the standard deviation for the population. So remember, we use the Greek letters to denote that those are the values for the population mean and the population standard deviation, not from samples. Okay, so now the question is, what does the distribution look like? So the distribution of SAT scores, or SAT scores in general, are discrete, but the normal distribution is theoretical. It's a continuous distribution. So most things in life, or most things that we'll look at in this course, are discrete distributions, and we'll approximate them with this continuous distribution. So the theoretical normal distribution for SAT scores, it would look something like this. So it has that bell shape, and it's symmetric, and it would be centered right there at 500. So basically we've got the mean right in the middle, right under the peak, and then, so what this is showing us is that students are much more likely to score around or very close to a 500, and then there's not that many kids that score out near an 800 or down by a 200. So basically the way that this goes is that usually right around here, right around that break in the bell curve, that'll be one standard deviation away. And since the standard deviation is 100, that would put us about at like 600. So right over here, put us down around 400. Out here would be 700, and then way out here would be 800. And the same thing going back. We'd have 300 about over here, and then 200 way over here. So now, like theoretically, with the normal distribution, it's a continuous distribution with a domain of negative infinity to infinity. Now, that doesn't entirely make sense on this situation because SAT scores are discrete and you can only get between a 200 and an 800. But again, sort of the normal model is this theoretical model that we use to approximate a lot of our discrete distributions. So we can do a lot of computations from the normal model using our calculator. So the way that this works is that the area under this curve, the area under the entire curve, is going to be equal to 1. So that means that if I kind of shade a portion of the area under the curve, that's going to give me sort of the proportion of students that scored within that particular range on the test. So let's say I wanted to answer the question, what are the chances if I picked one kid at random, what's the probability that their SAT score is between a 600 and a 700? So I wanted to answer this question. I want to know what percentage of students, or just if I picked one kid at random, what are the chances that I pick somebody that got an SAT score between 600 and 700? What proportion of all the students that took a particular test scored between 600 and 700? So the picture would kind of look like this. I've got 500 in the middle, so 600's out here, 700's out here. So basically I'm looking for this area right in here. So that area, that's going to be the proportion of students that scored between a 600 and a 700. And the calculator has the model sort of built in, so I can just ask the calculator to compute that area for me, to compute that probability. But I have to know how to ask sort of the calculator. So what I would be asking the calculator here is, I would say, okay, calculator, I want you to figure out that area for me. The function on the calculator is called normal CDF. It's the normal continuous distribution function. It's found under second and then vars. And obviously this is on TI 83s and 84s. So if you hit second and then you hit vars, you'll be in the menu and normal CDF is option 2. Pulls me up to the normal CDF. But now I have to know how to ask the calculator, like, to find that area. So I'm going to ask the calculator, I need to phrase this in terms of standard deviations from the mean. So I got to say to the calculator, okay, how many standard deviations away from the mean is 600? Well, the standard deviation is 100 and the mean is 500. So 600 is one standard deviation away from the mean because it's 100 above 500. So I'm going to use 1, comma, and then I've got to say how many standard deviations above the mean is 700. So 700 is 200 above 500, and the standard deviation is 100. So 700 is 2 standard deviations above the mean. So I'm going to evaluate the normal CDF of 1, 2. That gives me 0.1359. So if I wanted to interpret that answer, that's telling me I gotta go to a new slide. But what that probability is telling me is that about 13.6% of students score between a 600 and 700 on the math SAT. again, this is only true assuming that the distribution is approximately normal with a mean of 500 and a standard deviation of 100, which somebody told me that once. I should probably go and check to see if that's actually accurate. I've never read that on the official College Board website. But so let's try a slightly harder example. So let's say I wanted to know what proportion of kids score between, say, a 250 and 800. So I want to know what proportion of kids, what's the probability that if I picked one kid, they would score between a 250 and no, I'm gonna change this. I'm gonna change this to 650. So I always draw the picture when I'm doing these problems. Got 500 in the middle. 650 will be about out here. 250 will be about way out here. So I'm looking for all of this. So this area under the curve is going to be the proportion of students that score between a 250 and a 650 approximately. Okay, so what am I going to put in the calculator though? I've got to really think this over. So be normal CDF of, and I have to figure out how many standard deviations away 250 and 650 are. So 650 is 1.5 standard deviations above the mean, because the standard deviation is 100. So the distance from 500 to 650, that's 150 units above the mean, but a standard deviation in this case is 100 units. So if I'm 150 units above the mean at 650, and the standard deviation is 100 units, that means I'm 1.5 standard deviations above the mean. So similar logic for that 250, I'm 250 units below the mean, and the standard deviation is 100, so I'm 2.5 standard deviations under the mean, which I'll denote with a negative 2.5, because that means I'm 2.5 standard deviations less than the mean. And I can run that area on the calculator. Normal CDF of negative 2.5, 1.5. So that's going to be 0.927. So approximately 93% of kids score between a 250 and a 650. So what we need to get at here is sort of a systematic way or a formula to kind of compute the number of standard deviations that a particular value is from the mean, and then we have a name for that. We're going to call that a z-score. So if I take the difference between any value in the distribution and the mean, and divide by the standard deviation, that's going to give me how many standard deviations my particular x value is above the mean or below the mean. So that is called a z-score. I'll write down the definition. It's the number of standard deviations from mean. And if the z-score is positive, that means the particular x value is above the mean. If the z-score is negative, that means the particular value is less than the mean. It's also sometimes referred to as a standardized value. So sometimes somebody will say like, oh, what's the standardized value for somebody that scored a 650 on their SAT? That would just be the z-score or the number of standard deviations above the mean. that a score of 650 is, which is 1.5. So that's also called a standardized value. And these z-scores are unitless. So let's just look at one final example here. Let's look at one final example, which is not finding the probability that we pick a random student between two values, but let's find the probability that we pick one random student and they're, say, higher than a particular value. So I want to find out the probability that if I pick one random student, they get more than a 670 on the SAT. What percentage of kids approximately score a 670 or higher? So again, I'm always going to draw a picture. So here is the mean of 500, and I'm going to mark out 670. Now, 2 standard deviations away would be 700, so I'm not quite 2 standard deviations away. So that would be all of this area right here. So on the calculator there, I'm going to do normal CDF of, okay, well I need to find the standardized score or the z-score or the number of standard deviations above the mean that 670 is. Those are all synonymous things. So I'll find the z-score for 670. It's going to be 670 minus 500 over the standard deviation, which is 100. And that is going to be 1.7. So the area that I'm looking for is going to be starting at a z-score of 1.7, so you get an x value of 670, and I want to know all the area under the curve to the right of that. Now the theoretical normal distribution is continuous and extends on the domain of negative infinity to infinity. So really, I'm finding sort of the area under the curve from the right of 670, but all the way out to infinity. So really, I want to do this. But the problem is on the calculator, I don't have, well, the TI-83s and 84s at least don't have an infinity button. So just put a really large number there in for infinity, and that will be fine. Just put in a large number. So I would do, say, the normal CDF of 1.7 comma, and then I would just put in a couple of 9s. 99999, that's a large enough number. And I get 0.0446. So that means only about 4.5% of kids are scoring higher than a 670 on the SATs. Again, this is assuming that the scores are approximately normal with a mean of 500 and a standard deviation of 100. So this has been just kind of an introduction of kind of basic properties of the normal curve, a crash course on computing some probabilities using the calculator, and finding a z-score.